We are going to test the crankshaft and the camshaft position sensors on this vehicle. Whenever you're testing any type of these sensors, the first thing you need to know is what type of sensor you're dealing with. There are two types of sensors. One is a permanent magnet that generates an AC voltage. It will generate an analog waveform. And the other type, it's a Hall effect sensor. The Hall effect sensor will generate a square waveform. The main difference between them, it's when you look at the connector or wiring. The permanent magnet is a 2-wire sensor, and the Hall effect sensor it's a 3-wire sensor. So we'll look at what type of sensor we're dealing with. In this case, will be a Hall effect sensor. So we're going to look at a wiring diagram to determine which wire will be our signal wire, our reference voltage, and a ground. So those are the three wires you will find on a CKP or a CMP sensor that is Hall effect. A wire diagram is a representation of how the circuit is connected and how the circuit will normally work. When you analyze this particular wire diagram, you should always look at a diagram before you start testing, so you know which terminals are which and what to look for. So in this case, we have the crankshaft position sensor. It has 3 wires, terminal 1, 2, and 3. And notice that dashed line between those wires tells you that they're part of the same connector. So terminal number 1, red wire, goes to the PCM terminal 95, and terminal number 2 goes to the PCM terminal 49, and that is a sensor ground. So the computer supplies a ground to the sensor. And terminal number 3, it splices with the camshaft position sensor on the intake side, and it's also spliced with the map sensor, and it goes to terminal 103 at the PCM, and that is the sensor power voltage. So that's the power feed that supplies voltage to all these 3 sensors. And our signal is being received at terminal 95 at the computer. Now, if you look at these numbers, they're dashed line numbers. These numbers are all connected with dash line. At the end, it will tell you the connector at the PCM. So this is connector C100A. And here on the top, this is, even though it looks like a different connector, but it goes to the C100A as well. And here we have another one, is the C100B. So we have 2 connectors at the computer. So you could be able to identify to which connector the signals go to. And when you look at the camshaft position sensor, we know that terminal number 1 is a power sensor voltage. Terminal number 2, it's a ground supplied by the computer at terminal 51. Terminal number 3, it's a signal wire by the PCM, and that is a wire, a blue wire with an orange stripe. The camshaft position sensor on the exhaust side, terminal number 3, it's a gray wire with a black stripe, goes to terminal 74. That is the sensor signal. Terminal number 2 goes to PCM terminal 50. That is a ground supply by computer. And terminal number 1, red wire, goes to terminal 99, which is the power source, and it's also spliced with a variable charge motion sensor. So when you look at a diagram to try to identify your connectors, you can always be able to look at the connector. This is the connector C114. That's the CKP sensor. And this is the harness view. So when you look at the harness, you'll be able to see which terminal is which. It tells you here, harness connector. So the view of the harness. And right here states that terminal number 3 is the sensor power source at number 103. And this is the connector C100A, terminal 103. That's our signal wire. I'm sorry, not a signal wire. That's the power source. And terminal number 1 goes to PCM 90, terminal 95. That is your signal wire. So you should be able to identify terminal number 5 in this area. Terminal 49 is sensor ground. So this is where the computer supplies a ground at terminal 49. So that's how you'll be able to identify if you want to test at the computer to make sure that the signals are present at the computer, but you could also test at the sensor. So now that we have identified which wire is which, let's go and verify at the sensor. Because if we don't get a signal from the sensor, the computer will supply a reference voltage to the sensor. That could be a 5-volt reference. And the sensor is going to be grounding the signal on and off based on rotation of a reluctor wheel. So what you're going to be able to see, it's a different pattern, and that pattern is going to change based on year, make, and model, and it's also going to change based on how many teeth the reluctor wheel will have. So we're going to have to look at a reference waveform to determine how the pattern is supposed to look like. So you can be able to determine whether it's a good waveform or a bad waveform. But now, since we have a reference of where to start testing, let's make sure we're going to verify with a multimeter to see that this voltage values and grounds are present. Because if you're missing a ground, the sensor is not going to be able to work properly, or if you're missing the power sensor voltage. So if the signal is incorrect from the sensor, or no signal from the sensor, you got to make sure that powers and grounds are present. And then we're going to be able to check our signal. And that's what we're going to do first. Okay, so let's start by identifying the CKP connector and the terminals for signal, ground, and the voltage supply. So if this is our CKP connector, according to our wiring diagram, starting from the left to the right, we have terminals number 3, number 2, and number 1. According to our diagram, terminal number 3 is our sensor power supply. That's your reference voltage, which we should be able to measure 5 volts. The wire in the middle should be a ground, and terminal number 1, which is the one on the right side, should be our signal. Both wires on the left and right are red wires, but we could identify which one's which by connector ID. So we can start by checking for the 5-volt reference. You check this with the ignition on. The ignition is currently on. Our multimeter is set up in volts DC. The black lead is connected to a ground, and the red lead from the meter, we're going to check for a 5-volt reference at terminal number 3, and we should have 5 volts present. So 5 volts are present, and this volt should be constant, key on engine off, and key on engine running. Those 5 volts should be present at all times. No change in that voltage. Now the signal, it's the one on the right, terminal number 1, and we're getting a reference voltage from around 4.8 volts from the PCM. And what the sensor is going to do, the sensor is going to be grounding that signal on and off. So let's check our ground wire. The ground wire, it's a terminal number 2, and right now the meter is displaying 0.020 millivolts. Now if I change the black lead, I'm going to change the black lead and disconnect it from the ground side, and I'm going to connect it to the battery power side. So we should be able to measure battery voltage. And there you have it. 12.72 volts, that's battery source voltage. Now if I disconnect the negative side from the battery and connect it back to the negative side, now if I disconnect the negative terminal from the positive side of the battery and connect it back to ground, we measure 20 millivolts. So that's the ground. So we're going to back probe the signal wire. So we're going to go behind the connector at the signal wire, and this is where we're going to get the 4.8 volts reference from the computer. So we plug in our connector. Voltage stays the same, and when we crank the car or when the engine runs, that's where the sensor is going to fluctuate that reference voltage to ground on and off, giving us a square waveform. So we're going to see the measurements that we get from the multimeter but we are also going to test this with an oscilloscope, so you can look at the big difference between the meter and the scope. So let's go ahead and start this car. Sensor voltage remained the same. It just dropped to around 4.5, 4.6 volts. Now what happens if I switch this to our signal wire? Our signal wire remains at 5 volts constant. Not much of a change. So we go back to this is our reference voltage. We go back to our signal wire. Okay, so this is our signal wire measuring 4.8 volts is the reference voltage that the computer is applying to that wire. The job of the sensor is to ground the signal to 0 volts and back to that reference voltage. So you should be able to see a voltage dropping on and off. So let's see what happens when we start a car. With the engine running, the voltage only dropped to 4.6 volts, slight fluctuations on the millivolt side, but not much of a difference. You don't see it fluctuating on and off like a Hall switch sensor should do. And the main reason for that is because the multimeter is not fast enough to make that fluctuations. There are times where you just measure the average voltage that you will get from the reference from the computer, or sometimes you will get half of it when the engine is running, but not much of a change using a multimeter. That is why the best way to test a CKP sensor is using an oscilloscope. So we're going to hook up an oscilloscope and look at a waveform, which should be a square waveform, and let's hook it up and see what we get from there. So let's hook up the scope and let's see what we get. The way we have our oscilloscope connected is the black lead is connected to a ground, which in this case is to the transmission housing. The yellow lead it's connected to our signal wire from the CKP sensor. So now let's look at a waveform and see what we get. Here we have all 3 sensors together. Starting from the top, yellow channel is the exhaust camshaft position sensor. The green channel in the middle is the intake camshaft position sensor, and the blue channel on the bottom is the CKP sensor. We should be able to get a square waveform pattern as reference we have here. We should be able to get a nice square waveform pattern, as you'll be able to see. As you can see on this reference waveform for this specific vehicle, we should be able to get a nice square waveform pattern and a big square pattern here. That is the missing tooth on the relector wheel, and we don't see it. Or we have this uneven fluctuations. It's not consistent at all. Our multimeter, it's connected to the CKP sensor. Not really any fluctuations as much. Now if we move that the lead from the multimeter and we connect it to the intake manifold, not the intake manifold, but the intake camshaft, our meter fluctuates. It's going up and down, as you can see on our square waveform pattern. On all of it, you should see a nice square waveform pattern. but in this case we don't have that pattern as expected. This is our reference. The intake camshaft matches, but the CKP, the crankshaft, does not. So now let's go ahead and just review our recordings. We could start zooming out. This is our actual recording. If we zoom out, we should have a consistency waveform pattern as it was recommended by the manufacturer specs. Both the camshaft and the crankshaft position sensors do match, but if you look at the CKP, it's very, very inconsistent. So we definitely have a bad CKP in this vehicle. That's our main source of a rich mixture. So in this case, we have to replace the CKP sensor. I would recommend, after we replace the sensor, scope the new sensor. A new component, it means new, not necessarily good. So we should always test the component to verify your repairs and go from there. Alright, so with the crankshaft position sensor now replaced, let's start the vehicle. We're going to allow the scanner to record a little bit, or the oscilloscope, and then we'll review it after it gets recorded a certain amount of time. Now you can see the crankshaft position sensor has now a more square waveform. It looks more consistent, and once we pause it, we're going to be able to zoom out. Going to raise the RPMs too as well. We should be able to see the frequency increase. It means it's going to switch a lot faster. Let's go ahead and stop the recording. So now let's zoom back and look at the waveform a more consistency. If you can see here, now we have a recording where you can be able to see both camshafts on the top are switching a nice square waveform at the bottom. It looks more consistent, so if we get a little bit closer, we're going to be able to see that the crankshaft position sensor has our missing gap. This missing gap represents top dead center of number 1 cylinder. We zoom in closer, you can see it very consistent. Let's get a little bit closer. You should be able to see a square waveform pattern. And a lot closer. Very consistent. Way different than it was before. More of a nice square waveform pattern. There is a big difference between testing the crankshaft and camshaft position sensor with the meter. You can't really tell if you have really nice waveform or not. The meter cannot fluctuate as fast as in a scope, so that's why I always recommend to test the crankshaft or camshaft position sensor using an oscilloscope, so you could get a waveform and analyze the sensor a lot better. As you increase the RPMs, it should be able to increase the frequency. That means the timing of the switching from the sensor from 5 volts to 0, and it should be a nice square waveform pattern, because it looks a lot better now. The best way to check a CKP or CMP sensor is using an oscilloscope. A multimeter can only give you a voltage value, but it's not going to be able to switch as fast enough, and it's not going to give you very detailed information of what's going on. But a waveform pattern, you're going to be able to see if there's a problem with the sensor or reluctant wear or any kind of issues or interference.